In this series of lectures, we are going to explore acid and base chemistry in detail. And we're going to start out just by defining what acids and bases are. And we've run into acid-base reactions already. We've talked about them as we've talked about different types of chemical reactions. And we usually represent them as acid and base neutralization reactions, where we bring an acid and a base together and we neutralize the two, so it has a pH of 7. So let's start first with what's an acid, what's a base, and we'll talk about those neutralization reactions, and then we'll talk about dissociation reactions after that. So in general, acids, when we encounter them in our daily lives, are going to have a very sour taste to them. So my mind immediately thinks of lemons or oranges, things that are tart, have a lower pH. They're acidic compounds inside them. Now, strong acids can dissolve metals. They're really good at that. They'll neutralize bases, as we talked about. And one of the ways as chemists that we know we have an acid when we're in a lab setting is we can use litmus paper, which will, blue litmus paper will turn red, or the universal litmus paper will still turn red when you have a acid present in a solution. Now, some examples of this include hydrochloric acid, which is going to be a strong acid. We'll talk about acid strength and weakness later on, but this is a strong one. Yay. Acetic acid and citric acid are ones that are weaker. Citric acid you'll find in fruits, also a lot of beverages. Acetic acid is essentially household white vinegar. So I use this for cleaning, I use it in my laundry, and sometimes I also use it in recipes as well to cook with. So those are kind of some of the common ones. Bases, on the other hand, rather than tasting sour, they would taste bitter. So they would have a very bitter taste. And they would feel slippery. So if I spilled a little base on my hand, it would feel very slippery to the touch, like soap. They'll neutralize acids. And in the lab, when we want to find out if something's a base, we'll look for red litmus paper turning blue, or universal litmus paper turning blue as well. And so some of the common ones for these, sodium hydroxide is one of our classic examples. And we use hydrochloric acid and sodium hydroxide a lot in the lab, and we'll talk about it a lot in this series of lectures. Common ones that you might actually know about already is sodium bicarbonate. This is actually baking soda. So I use that in my kitchen a lot, again, for cleaning, but also for baking. And ammonium, which I use for cleaning, not for baking at all. But it's really useful for cleaning. It's in a lot of cleaning products. And so these are kind of like the way we experience these in our daily life. You are running into acids and bases all of the time. And in the lab, they're extremely useful for synthetic transformations as well. So looking at this a little bit deeper, as we define these, we'll walk through actually several different definitions of what an acid is and what a base is. So one of our fundamental versions of fundamental definitions. And I'm gonna layer definition. So that way I'm gonna give you a definition that encapsulates some acids and bases, and then I'll give you a broader one and a broader one. The first one I'm gonna start with is the Arrhenius definition. And it states that acids produce H+ ions in solution, and bases will produce hydroxide ions in solution. So that hydroxide ion is an oxygen covalently bonded to a hydrogen, and it has an overall negative charge. And so this is what it would look like if I were to draw out its Lewis structure. Now an H+, a hydrogen ion, right? A hydrogen ion is just a proton. Like a hydrogen atom has one proton and one electron, no neutrons. So if I remove that electron, I just have a proton. So we're talking about something that takes up like a negligible amount of volume. It has a positive charge, but it is itsy bitsy. I mean, the hydrogen atom itself was really small. And so what we'll talk about a bit later is that it's very rare if you have something in water that you would have H+ ions around. They would most likely connect with a water molecule and become a hydronium ion. And so anyway, and any acid is any sort of chemical that will undergo a reaction that produces these H+ ions, these protons, and a base will produce hydroxide ions. And this characterizes kind of the basic chemistry lab acid and base. Hydrochloric acid, it'll dissociate into H plus ions when it's in solution. And sodium hydroxide, which is an ionic compound, right? And so we have our metal sodium, and then we have our anion, which is polyatomic ion hydroxide. And so looking at what happens if these are in water, once we have our remember, this H plus is just a proton, and that's it. It's so little. If it's in water, remember in the liquid state, these are molecules that are really close to each other and tumbling all over one another. And so to have a proton injected into this essentially like mosh pit of molecules, it isn't going to stay alone. It's a single positive charge that will be attracted to a lone pair on an oxygen in the water that it is in. And so what happens is a bond forms in between these. The lone pair on an oxygen, which remember is going to be partially negative already, it has pretty electronegative bonds to these hydrogens. They'll be partially positive. Will actually formalize a bond, and that hydrogen proton or that hydrogen ion proton will be attracted to that electron density. Plus and minus are attracted to each other. And will form this ion, this positive cation that is a hydronium ion right here. H3O plus is the way we'll write this. So we can interchange H3O plus and H plus for one another. This is, if it's in water, it's interchangeable. So when we think about neutralization reactions under this definition that Arrhenius developed for acids and bases, we kind of go back to that original definition we talked about with chemical reactions, that usually when you have an acid and a base together, they neutralize to form a salt and water. So that water piece right here, that's coming from the H plus ion that's formed by an acid, and the OH minus, the hydroxide ion that's formed by a base. And together these combine to form H2O. And that's where we get our water. And so then the salt component is whatever is left over. So in this particular case, we're bringing together a hydrochloric acid and sodium hydroxide. We're bringing together the chlorine ion that's left over, so a Cl minus, when we produce the H plus, and we'll have a sodium cation left over after it dissociates from the hydroxide ion. And so we'll have Na plus and a Cl minus, and these are going to combine to form sodium chloride. So that salt formation piece of this reaction right here is coming from what's left over from the acid producing a hydrogen proton and our base producing a hydroxide anion. All right, so let's broaden our definition a little bit. So that's a useful definition, but we find that there are more acids and bases than just those that produce hydroxide ions and protons. The proton piece is actually will stay a common thread for a while. So a Bronsted-Lowry definition states that an acid is something that is a proton donor. It will be able to lose a hydrogen atom as an ion, a positive ion, into a solution or to a base. And then a base is something that accepts that proton. So it's something that can form a bond to a proton. In our last case, it was that hydroxide ion. It had lone pairs that could form the bond to the H plus ion that was formed by our acid. Now, this is a broader definition. This is actually going to be the most commonly used one. It's not the broadest definition we have, but I think it's the one that we use the most, especially in introductory level chemistry. And so in these cases, when we're looking at chemical reactions, what we're really looking at is within our acid, we're looking for an acidic hydrogen or a hydrogen that can become a proton through a chemical reaction. And what happens there, what's really happening there is a bond is breaking, right? This HA bond is breaking. And then our base typically has a lone pair that can form a bond to that ion that was just formed. So here it's this lone pair on our base. And we're generalizing these as B for base and A for acid rather than giving you concrete examples, but we'll do that soon. So that lone pair is key. So when I form this bond right here, so my acidic hydrogen breaks apart and that hydrogen is donated. It's gone. The bond broke, that part of the chemical reaction has happened. Now a bond is going to form. A bond forms between the hydrogen and the base. This is why we need a lone pair, not one electron, because to form a bond, right, a bond is going to be 2 electrons. Both of the electrons in the bond are going to be donated from the base to the proton, the acidic proton, to form a new bond between that hydrogen and the base. And so that's why we really need to have 2, because every bond is formed at least with 2 electrons. And so they're both going to come from the base. So a lone pair is perfect. A lone pair can, if a proton comes by it can form a bond just through that electrostatic attraction between the electron's negative charge and the proton's positive charge. So we can look at our previous example, right? And we can see that the Bronsted-Lowry definition applies perfectly to this still, just like the Arrhenius definition did. Our HCl is going to be our hydrogen donator, right? Here's our acidic hydrogen. And our sodium hydroxide, the hydroxide piece, the oxygen is going to have a lone pair that can be our H plus acceptor. So remember, this hydroxide has 3 lone pairs and a negative charge, which is going to be something that a positive charge would be extremely attracted to. Like already the negative positive charges are attracted by Coulomb's law, but then having 3 lone pairs that could form that bond to the proton is really favorable. And so one of these lone pairs is going to be the component of the base that's accepting the hydrogen. And then we form our salt in our water after that. Now, the nice thing about the Bronsted-Lowry definition is that it encapsulates more acids and bases than just our Arrhenius definition. And I've got an example down here. So here we're looking at sulfuric acid and ammonia combining in an acid-base neutralization reaction. So our hydrogen donor is our sulfuric acid. We have one of these hydrogens will be donated. And then within our base, it's actually the nitrogen that's going to be able to do the hydrogen accepting. And sometimes it's helpful to look at this with Lewis dot structures. So let's do that. So here's our sulfuric acid. Our sulfuric acid is going to have a hydrogen that it can donate, right? And we're going to add to that this nitrogen that has a lone pair that can form a bond to it. So I'm actually going to get rid of this plus sign. And so what happens is this bond here breaks and a new bond forms. And then we produce our HSO4 minus and NH4 plus. Now I'll note something. When our bond breaks right here, when our bond breaks in our acid, it's going to be what we call heterolytic cleavage, which it's a word for another day. But what it means is that both of the electrons in the bond between the oxygen and the hydrogen, they both stay with the oxygen. Now, a homolytic cleavage would be where each one keeps an electron. And so in these acid-base reactions, both of those electrons stay with the oxygen, which means at the end of my reaction, I leave those 2 electrons here. And so it's kind of like it's formed a bond with the hydrogen, broken the bond, but kept the electron that the hydrogen contributed to the bond. And so it gains a negative charge. And so then we see that negative charge for what's left over from our acid. And then our base has this lone pair and it's neutral in this case. And when it forms a new bond to something that has a positive charge, it's essentially contributing 2 electrons rather than 1 into a shared bond with a 1 coming from something else. Since it's doing all the work of adding 2, it's taking on a positive charge overall, or forming that bond to that positive ion is allowing it to then have an overall positive charge at the end. And so here we can see that our old Arrhenius definition wouldn't work. There's no hydroxide ion taking place in this reaction, but we are seeing a proton essentially transfer from an acid to a base. And that's how I think of acid-base reactions, is that typically there's a proton being transferred from an acid to a base. And that'll cover all Bronsted-Lowry acids and bases, and it'll cover all of our Arrhenius acids and bases. Now, it still won't cover all acids and bases, because we're going to talk about Lewis acids and bases much later in this lecture series, where we're going to talk about this as really just about electrons moving around rather than protons.